Hello.
Hi, Dr. McKibben. How are you?
Good. How are you doing?
Well, thank you.
Six. All right. Good afternoon. So we have two folks missing today, and they will not be able to join us. So it's just us for today. So I have a couple of thoughts, questions for you guys that I want to pose before we get started with anything else. First of all, I have a concept checklist for the exam that I'll give to you guys. I'll post it after we talk today. It's just a checklist, but it can be helpful just to review the concepts that we've gone through so far. We also have an exam scheduled for next week. However, I am thinking we might be better off pushing it back a week. Okay, I see a couple of nods already. um, if anyone, is anyone really, okay, yep, okay, is anyone really opposed to that? I can tell you why. Okay. Basically, the material that we'd be covering today, which is the paired samples t-test or the dependent samples t-test, they're the same name, along with the Wilcoxon, is the last material on the test. And I hate for you to have that material and then jump into the test. So I'd like there to be a week in between where we can make sure that those concepts are okay with you. So the, and then as you probably already noticed, Lindsay, who was going to do our talk today on t-tests for independent samples, is one of the two folks who can't be with us tonight. And I'm hoping that, if this plan is good with everyone and we're good to do this, then she can talk next week. So I think it works there too. But I think it would just be good. I just want to pad it a little bit with that week for some. We'll still talk about new material, but that week for review as well. I'm going to shut that curtain because I can see I'm just glare right now. So give me 1 second to do that. But no, that didn't really help, did it? Maybe because I didn't get this really over. I feel like I'm getting everything but the glare. Okay, hopefully that's a little better now. Okay, so that's my thinking. I don't see a real downside to it, but if it's, feel free to chat me privately if you think that's problematic for you, and I'm sure we could figure something out. But I think that's the best thing. So if we do that, and I'm assuming we are, because so far I'm only seeing agreement. If we do that, then I want, can you just remind me who's doing the Man Whitney U article? That's you, Justin?
Correct.
Okay, so I think you were probably then scheduled to do the Man Whitney U reporting the week after the exam. Is that right?
I can't remember, but I think that sounds right.
My question, and you can think about this, and we can talk like just one-on-one later. But my question would be if you would be able to do that next week along with Lindsay, and then we'd kind of be up, because then it wouldn't make sense the other week. You know what I'm saying?
You're saying because we would be taking the test that week, I should do it.
Right, exactly. And I don't want you to have to do it the same day as the test.
I understand. I'm completely fine with sharing that time with Lindsay next week.
Okay. Yeah, I mean, there'll be enough time for each of you. No problem. Great. It just means pushing up for you a little bit, so that's why I wanted to give you time to think about it.
Yeah, no, I'm completely fine with that. Not a problem.
Okay, great. Wonderful. Okay, so I think we then have a plan. Yeah, Jenna, what's going on?
Do we have to submit anything the weeks we're not presenting? Like the fill out the form for non-presenters, is that something we submit or is it just for us?
No, it was something that I was going to have you submit. I did push back the date, and I'm going to push it back so that you can submit the one for Man Whitney, and the one, if you're not presenting, you would submit the one for T-Test for Independent Samples and Man Whitney U next Wednesday.
Okay. And then what are we supposed to do during our presentation? Is it just answering the questions on the presenter's guide or something?
Yeah, that's pretty much what I'm looking for, is for you to kind of have a little discussion with those questions being answered as part of that. And usually people find interesting things in the article that they say that they want to point out, or, you know, those sort of things. So yeah, you're pretty much going through those questions, but in a slightly more discussion format. It's like in a way that we can understand what your takeaways in the results section of the article were. But like something I talked about with Lindsay this past week is she saw a problem in the design issue, and she wasn't sure if she could bring that up or not. And I was like, yeah, definitely feel free to bring that up. Because I agree that's an important issue, and even if it occurs earlier on, it's still going to impact your results. You know, so I guess that might be the little exception, is if you see you know, an interpretation or something that you want to comment on, feel free to do that. And
Thank you.
okay, and we can talk more offline and one-on-one if you have like specific questions about your article, or you want to show me your, you know, what you're doing, or that sort of thing. Okay, so given all of that, so yes, so for most weeks when we have an article, you'll be putting something forward for that article in addition to whatever homework you might have for that week. Okay. And then, of course, that's why another reason why I'd like to avoid having an article on exam. There's a few reasons why I want to avoid having articles on exam days, if at all possible. But that's another reason. I don't want you to have anything really due then, at least for the article part. So, given that, where would you like to go today? The choice being, would you like me to go through the last two tests that we're going to cover for the first exam, which is the paired samples t-test and the Wilcoxon, and then you have everything at your disposal, and we will still have time to do a bit of a review today if you have questions? Or would you like to spend, and then you have time next week to kind of recapture that, or would you like to spend today entirely on review, on just asking you questions and review stuff and those sort of things and catching up to that point?
I think
see
I'd
what I'm saying?
rather do the review next week so we have time to like ask questions about any of the stuff from today.
Okay, that makes sense. Yeah, okay, fair enough. Let's do that then. So let's at least look through the material for today, and I did post it, although I posted it very close to the time, right off on D2L. So if you're on D2L, you should be able to find the lecture for today. Let's go through that. It's actually not very long, and it's not very different than what we did last time. There's a couple of little tweaks, but it's not too bad. And then we can still take some time to answer any questions, and then next time we'll jump in and do more of a review yet. Okay. So let me then share my screen with you guys, which I think it might have closed on me. Give me 1 second. Lecture. Okay, here we go. And here, not here. Oh boy. Sorry, it's not taking. Here we go. Okay. Okay, hopefully you can now all see the PowerPoint. Okay, so I do have a reading that, you know, if we have time next time, we might start talking about One-Way ANOVA and Friedman. Let's see, I want to make sure we have enough. We'll prioritize review. We'll prioritize review. If there is still time and we feel up to it, we might talk about that as well. Okay. Your homework assignment will be the same, essentially, pattern as last time. You're going to answer the same sort of questions, except I'll give you 4 new data sets. Okay, 4 new situations. And then if you would all look at, if you haven't done so, all look at the T-Test for Independent Samples article, and all look at the Mann Whitney U article. And for those of you not presenting, please complete the document I found out there for non-presenters. Okay, and then if you are presenting, there is a document for presenters, which you can, and it's your choice whether you want to just answer all the questions through the PowerPoint and then not submit that document, or if you'd like to make the PowerPoint a little bit different and then just submit that document to make sure you got the questions covered. Okay, so you could do it all in one through a PowerPoint if you so desire. Okay. And if that doesn't make sense, just talk to me later and I'll be happy to go through it with you. So this time we're talking about the paired T-test and the Wilcoxon signed rank test. So if you remember from last time, the T-test for independent samples was comparing 2 independent groups, 2 completely separate groups. And the Mann Whitney U basically did the same thing, except that was what you used if you didn't meet the assumptions for the independent samples T-test. So they were both had the same purpose. Just like today, the paired T-test and Wilcoxon test both have the same purpose, and that's to compare repeated or paired samples. Okay. Just skip something. So this time we have 2 scores for each person, and you're comparing one group of people to themselves. So one of the simplest examples we can probably go for is a pre-post with treatment example. So look at depression levels before treatment, instituted treatment, look at depression levels after treatment, right? So then we'd have 2 scores for each person. Before treatment depression score, after treatment depression score. And in this analysis, our goal is to understand, was there a change? Was there a change? And just like the t-test for independent samples and associated Mann-Whitney, here you can also have a 2-tailed test or a 1-tailed test. So a 2-tailed test might be, did the person change? Or there will be change in those undergoing the depression treatment. We're not saying whether they're going to get better or get worse. We're just saying there will be change in the depression scores in those undergoing the depression treatment. So we could also have it be 1-tailed. With a 1-tailed example, we might say post-depression scores will be lower, right? Which we might expect. We might expect that they improve after a treatment. That would be good news. Or if we feel that this is a very poor treatment, let's say, we might say that we expect scores to be higher after treatment, right? We might expect symptomatology to go up after treatment. And maybe we could put in something else other than treatment, but I think you get the idea that we could be lower or it could be higher. Okay. Okay. So here's our example with the treatment. We have the before, the after. This is kind of just giving you a little bit of a highlight as to some way you might sometimes see it in a journal article. If it's a pre-test, post-test design, you might see it as OXO or O1XO2, where O is the observation, the data gathered, and X is the treatment. So this is just a little bit of, we'll cover this more in during next semester, but I just thought I'd point it out in case you run across it as you're reading articles or that sort of thing. So in other words, the first O, let's take the O1XO2 example. The first O1 would be measuring depression at time 1. X would be the depression treatment. And O2 would be measuring depression at time 2. So we could think of it, if you want to go with the BDI, for example, BDI before depression treatment, BDI after. Okay. All right. So the paired t-test is going to compare the mean from the pre-test to the mean to the from the post-test. Okay. So it's trying to understand if there is a significant change from pre-test to post-test. And if our alpha is 0.05, then we are looking for p less than 0.05. If our alpha is 0.01, we're looking for p less than 0.01. In other words, alpha and p match. Okay, and that's true for any test. So I'm just highlighting that, but that's true for any test, that you want your alpha and your p to match. Whatever your alpha is, I want my p to be less than that. Because if you remember what p is, it's really the probability of a type 1 error. So I want that probability of a type 1 error of a false positive to be low. Okay. Let's keep skipping ahead. Sorry about that. Did it again. Okay, so this, don't worry about this. This is only if you find this kind of thing interesting or helpful. I just thought I'd point it out. This isn't the kind of thing I'll put on the exam, let me put it this way. But I just thought I'd point out in case it's helpful to you to just see how this kind of thing, how these different scores develop. And the only things I really want to point out are the similarities here. And that is in the top, what we're doing is we're looking at subtraction of means. So when we have a z-score or t-score for a single sample, we're looking at the sample mean minus the population mean. When we had our t-test for independent samples, we were looking at a one sample mean minus the other sample mean. And now that we're doing a dependent samples t-score, we're looking at the difference mean for the sample minus the population difference mean, which is assumed to be 0. So we're really looking at the difference mean for our sample. And on the bottom, again, this may be less familiar, but it's a standard error of the mean measurement. So they're really all quite similar, and they're just getting at different things. And that's my main point here, is that they all just have slightly different purposes. If you remember, the z-score and t-test for a single sample are trying to compare a population to a sample. Population mean, sample mean. The t-test for independent samples is trying to compare 2 independent groups or samples. And our t-test for dependent samples is comparing 1 sample to itself. Okay, so enough about that. So now if we start looking at how we want to do this, I want to point out that the way you set up the data is that you're going to have 2 scores for every person, right? That's what we agreed to. So each ID or each whatever has 2 scores. Each person has 2 scores. And the way we typically set up data, I'm going to say typically because if you've done some advanced data work, you may have seen it set up a different way. But typically it's 1 row per person or 1 row per participant. So person 1, in this case, has data at the pre-test in March and the post-test in April. So that's a good way to, even looking at data, to start thinking about which kind of test am I going to run, which way was it set up. Right? Because for the t-test for independent samples, we only had 1 outcome, 1 big measure we were looking at for each of our groups. Here, it's 1 group, 2 measures. Okay. Okay, so here's a typical pre-test, post-test design. We have our pre-test mean, treatment, post-test mean. Okay. And in this case, when it was run in SPSS, we presume, the P was 0.011. If our alpha was 0.05, this would be significant. And again, it looks like, I don't know if this was run as a 2-tailed or 1-tailed test, but the same rule applies. In other words, if it's 2-tailed and you get your p-value, let's say this came right out of SPSS just for fun, and this is your p-value, 0.011, and your alpha was 0.05. Okay, so you're good. Your p was less than your alpha, 0.011 is less than 0.05, we're in good shape. We're going to reject the null. If this had been one-tailed, you still have to get the direction correct. So if I said that people's scores would decrease at post-test, I'm in good shape because they did. 88 goes to 86. 86 is less than 88. It decreased. If I said scores would increase from pre-test to post-test, I'm in trouble. I cannot reject the null. That's not what I predicted. So just like for any other test, when you have a one-tailed test, you have to get the direction right. So just like for any other test, when you have a one-tailed test, you have to get the direction right. Okay. Yeah,
If the p-value is greater than 0.05, you fail to reject either direction.
correct.
Okay, so if it's less than 0.05, that's when you need to make sure it's the right direction and the only way.
Well, yeah, that's a good point actually, Jenna, because if this came right out of SPSS and this is the two-tailed value, so let's say it was 0.06, right? And it's the two-tailed value, you have to chop it in half first.
Yeah.
Then it's 0.03, now it's less than 0.05, now we have to evaluate the direction.
Okay. But still, after the division, it has to be less than 0.05 and then in the right direction to reject the null.
Reject. Yes.
Okay.
Yes. Yeah, that's absolutely right. And that's all assuming our alpha was, of course, 0.05. If our alpha was 0.01, we would be done at this point, right? We have nothing to look at here because 0.011 is not less than 0.01. So always p less than alpha. And alpha most of the time is set to 0.05. So yeah, you're absolutely right. But I'm just pointing that out to be aware of it. Okay. And here's our little comment on this, that the post-test is significantly lower than the pre-test, suggesting that the treatment was effective in lowering the score. Okay. Come back here. Here, this one's an easy one. P equals 0.396. I don't care if it's two-tailed or one-tailed. If I divide that by 2, it's still not getting anywhere close to 0.05. There is no way I'm going to reject the null. This is not significant. And it says here, and apparently they're looking at this as a one-way test because they're talking about lower. The post-test is not statistically significantly lower than the pre-test. They should have really reported this P, assuming this is the two-tailed P from the SPSS output, then they should have cut this in half. Right, because the P value from the SPSS output will always be two-tailed. So they probably should have reported this as half of that, if that's true. Okay. Question on that? Or anything so far? Okay. All right. All right. So now let's look at this. A researcher wants to determine if installing brighter energy efficient lighting on April 1st will reduce, right, residential crime rates. So that's already giving us our clue as to whether this will be one-tailed or two-tailed. So what are we going to do? We're going to gather data for March on crime. We're going to have the brighter lighting installed on April 1st, and then the crime data will be gathered for April. So pre-test, treatment, post-test. Okay. So hypotheses here could be taken right from the example. And I want to point that out because I really want you to get hypotheses down. So The alternative could be installing brighter, energy efficient lighting on April 1st will reduce residential crime rates. See how I pulled that right from the example? I just started with the word installing and read it. And then the null, just add the word not. Installing brighter, energy efficient lighting on April 1st will not reduce residential crime rates. So that's how I get my hypotheses. Okay. Do I have a, yeah, sorry. Ignore this slide for the moment. I made a slightly better slide. So it's this next, so sorry, ignore this slide that says paired t-test and just go with the next one that says paired dependent samples t-test. There's nothing wrong with the other one. I just made this one slightly better and forgot to remove the other one. So one IV that consists of two categorical related groups or matched pairs. We have one continuous DV. We have to make sure there's no outliers this time for our difference scores. So what we're going to do is we're going to remember, I keep saying we're going to look at change, we're going to look at difference. Well, we're going to actually use SPSS to get the difference between every pair of scores. And then we're going to look at that, and we don't want outliers there. And we also want our different scores to be normal. So the good news, bad news here is that you only have to look at one set of scores this time. Last time you were looking at two sets of scores, right? For like treatment and control, or for the bamboo plant and the no plant. Now you only have to look at one set of scores, your different scores, but you have to calculate that first. You have to get your different scores in order to be able to look at them. Okay. So how are we going to do this? We're going to learn how to compute in SPSS, and we're going to compute a difference variable. So we're going to name it difference or diff. And then we're going to say that equals post-test minus pre-test, or April minus March. Now, a question that comes up here, can you subtract pre-test minus post-test? Can you do it the other way around? The answer is sure. It kind of doesn't matter as long as you know what you're expecting in the end. So if I subtract post-test minus pre-test and I get a positive mean, that means that my post-test scores were higher than my pre-test scores. If my difference mean is positive, then that's what that means. If I get a negative difference mean, that would have meant that my pre-test scores were actually the higher ones than the post-test. So you can subtract any way you like. Just be aware of how your different scores will come out. And I think SPSS kind of helps you with this a little bit. So we'll look at that in a moment. Okay. So here's how you actually compute a variable. We haven't used this one, I don't think, yet. Oh, no, you have. You did a little recoding. So excuse me. I think you have used transform before. But it's transform compute variable. Transform compute variable. And then this is what pops up down here. The target variable you have to enter. Whatever you'd like to call it. Difference, change, whatever you like. And here we've decided we're going to subtract post minus pre. So we have some choices here. We can type in, I would just bring over the variable. So I would bring over April, hit minus or hit the minus down here. There's a whole bunch of symbols down here, including a minus sign. And then bring over March. If you would want to subtract March minus April, just bring over March, hit the subtract sign, then bring over April. When you've done, yeah, of course, please.
So I know you said there's not a huge difference between subtracting the pre from the post or vice versa. Is it that you're getting an absolute value for when you're comparing, or why?
No, that's what I'm saying. You're not getting, it's a good question. It's a great question. You're not getting an absolute value. So I just want you to be aware of whether you expect, how you expect it to come out based on how you subtract.
Got it.
Yeah. So yeah, that's a very good question because the different score will just be the different score. So you could do it so that it always comes out positive. You could like say, okay, I'm expecting my post to be higher because I expected improvement, so I'll do post minus pre, or I expect my post to be lower because I hope the depression scores have gone down, so I'll do pre minus post. Okay, so you could do it that way always, as long as you know, have in your head how you expect it to come out, you're fine. Okay. Good question. Okay. Here's our new diff variable, and you can see this right here. That actually it looks like crime rates went down in April, at least, you know, somewhat. We'll see if it's actually effective. And so because they did April minus March, they got a whole bunch of negative numbers. Nothing wrong with that. That's perfectly fine to work with, just how they did it. Okay. All right. So you're going to follow the same procedures as in the t-test for independent samples to test for outliers, box plots, and normal. Normal, really, we're not looking at skewness and kurtosis or the QQ plot or the histogram. We're primarily looking at Shapiro-Wilk. So you don't have to worry about that other piece. You can look at them. There's no harm, but I think if you just look at Shapiro-Wilk, that's sufficient. And then here's the exception. Now, remember how you had a dependent variable and a factor variable before? You're still going to have the dependent variable. That will be your difference score, but there'll be no factor variable. So you still have your dependent variable, but there'll be no factor variable.
I have a question.
Sure.
This goes back to the t-test one. So are we supposed to look at, for normality, all of the skewness, kurtosis, Shapiro-Wilk, all of that? Or can we, because I was just using Shapiro-Wilk stuff.
Yeah, that's what I was saying. You can just use Shapiro-Wilk, yeah.
For the t-test one too? Or the independent samples one?
Yes, yes.
Okay.
You can just use Shapiro-Wilk. Box plot, Shapiro-Wilk will get you through.
Okay, sounds good.
Okay. Okay. And then this time to run our pair t-test, we click Analyze, Compare Means, and then as opposed to choosing independent samples t-test, we now choose paired samples t-test. All right. You then move your pretest or whatever one to variable 1, and your post-test to variable 2. Right, so you see how they moved March under variable 1 and April under variable 2. You click OK, and this is what you get. It actually will give you the mean for March and the mean for April, so you can compare it here. Okay. And then here's your paired differences with your T, your DF, and your sig value. Now, this is actually a very interesting point that came up here, because our sig came out as 0.000. Well, we don't actually ever really have a probability of 0, despite what this says. In fact, if I could click inside it, it would be something like 0.00001. In other words, it wouldn't just be zeros. There would be another number. If I went far enough out in the decimals, there would be a number there. It's not going to be just 0. So whenever you see something that's 0.000, you should report it as p less than 0.001. And that's for any test. Going backwards, going forwards, any test. So you never want to report p is 0. And that's because it's simply not true. Now, if you want it to be fancy, you could go and click this, and then you could report p equals 0.0000012, whatever, if you really wanted to. But pretty much people don't do that. Pretty much people just, when they see this, they write p less than 0.001. Okay. All right. So this is again how it came out, and they shouldn't have put this here either. I mean, this is an example of not doing it right. This looks like their actual table. I thought this was their output, but now I'm looking at it again. I'm like, this is their actual table. So they should have put t less than 0.001 here. But in either case, they can see that there was clearly a reduction in the crime rates. Okay. Now, again, if this had been a two-tailed test, if they had just talked about a change in crime rates, then when it comes to resolving the hypothesis, you should only talk about a support for change in crime rates. And that's a tricky thing, because I think people mostly do talk about the reduction. So it's a technicality, but I wouldn't get you on that technicality, but I'm sharing it with you. That typically, if your hypothesis is about change, you should really talk about change. In this case, their hypothesis was about reduction, so they're well placed to talk about reduction. But I think people run two-tailed tests all the time and talk about the direction. Yeah. Okay. This little guy here is talking about how you can get an effect size for, for your analysis. And it is helpful to have some sort of effect size, or I'll show you a different method in a little bit. So I would say pick one of these two that I'll show you as something that you'd like to report. And the effect size is simply the mean difference and the standard deviation of this difference. And I'll show you where those two are in just a moment. So you just take the mean over the standard deviation. That gives you your D, or effect size. Okay. So it's a really nice, simple way to get that. Okay. So I want to show you, here is your mean of change. Here is your standard deviation of change. Right with the paired sample test. That's where your mean and standard deviation are. That's what you'll divide. Okay, mean, standard deviation. Okay. All right. So then if we do that, this would be a potential write-up of how it could look. And this is kind of a detailed write-up, I'll give you that. It comes from Laird, but I just thought it might be helpful to kind of look at it together. So a paired sample t-test was used to determine whether there was statistically significant mean difference between the distance ran when participants imbibed a carbohydrate protein drink compared to a carbohydrate-only drink. 2 outliers were detected that were more than 1.5 box lengths from the edge of the box in a box plot, and they decided that inspection of their values did not reveal them to be extreme, and they were kept in the analysis. Okay. That could have, another way they could have gone is, of course, to have done the Wilcoxon that we have yet to talk about. The assumption of normality was not violated as assessed by the Shapiro-Wilks. Participants ran further when imbibing the carbohydrate protein drink as opposed to the carbohydrate-only drink. A statistically significant mean difference of 0.136. This is the 95% CI, this is the T, and this is the D value. So a couple things worth pointing out here. First of all, they do report the P for the Shapiro-Wilk, which is it's a good idea. They didn't have to. And they report everything about the box lengths and how that was violated. So it's nice that they went through the assumptions like this. Yeah, I guess I just wanted to make sure you guys are feeling okay about reporting these T things and the D and all that kind of stuff. So let me show you. Okay, good. Let me show you where it comes from real quick. Just, oh, I can't because I don't, I can because I can switch screens and show you that in a little bit, show you where it came from if anyone wants to see that. So T parentheses, this is the DF. This is our actual T value. This is the P, which is correctly reported in this case is less than 0.001. And they got the D by dividing the mean over the standard deviation for the difference. Okay. Any questions, please feel free to ask me either now or later. Okay. Here's the other thing you could do. It's a change percent formula. If you don't like the D, you could do this. In addition to discussing mean reduction of 65 from 407.88 to 342.88, it can be expressed as a percentage change. Okay. And so the triangle is often called delta, which you may know from, just Greek language and that sort of thing. And delta often represents change. So that's why this is change percent. Or percent change. So here's how it works. If you want to get a percent change, you take the new value or the post-test minus the old value or the pre-test divided by the old value times 100. So in this particular example, we had 342.88, the old mean, sorry, the new mean, minus 407.88, the old mean, divided by the old mean, 407.88 times 100. And we just work our way through. So we take the negative 65 we got, we divide by the 407.88 and multiply by 100. Here we've done the division, 0.15 negative 0.1594 times 100, which is negative 15.94, which basically means change went down 15.94%. Okay. Yep, negative indicates a decrease, positive signifies an increase. Okay. All right. We detected a 15.9% decrease in the crime rate in April after the lighting was installed. That's how you would talk about that. So it's nice. It's nice to know this. It's helpful. I would say do either the, I figure probably most of you will choose the Cohen's D to report, but this is a nice thing to report too. Just choose one that you like when reporting results. Okay. Okay. So the Wilcoxon test. This is the alternative to the paired t-test or dependent samples t-test. And it's used when you either have outliers or when you have a substantial departure from the normal distribution criterion. So it really should include outliers here. We talked about the pretest criteria. If you don't meet those pretest criteria of no outliers and normality, you're heading for a Wilcoxon. Okay. And here's something showing, of course, if you don't have normal, this is when we consider the Wilcoxon. And again, outliers also. Okay. So this, here we go again with this showing the legacy way to do it. But I think all of you are updated enough that you don't have to do the legacy way. So let's look at this and then I'll show you real quick the non-legacy way. So to do the legacy, well, actually, to do the non-parametric, you have a choice. You either go to legacy dialogues and 2 related samples down here. If you were doing it the non-legacy way, you would just go non-parametric related samples. That would be the non-legacy way. Okay. Move March to variable 1, move April to variable 2, check off Wilcoxon. Click OK. And here's what you would pretty much get. And that's why I prefer that you not use the legacy unless you do have a version old enough where you really have to, because you don't get a lot. You just get the Z and the p-value. So I prefer you get more information. P less than 0.001. Notice again how we take that, because that says 0.000, report as P less than 0.001. And that indicates a statistically significant difference. Okay. And then this is one way you could report the Wilcoxon test. I'm going to actually flip over, if I can, to Laird, so I can show you. And this was extra stuff. I'll just leave this here. But basically, as you can see, we're comparing medians, and then we're reporting the Wilcoxon number, the Z, the P, and the R. So, like I said, let me leave this up here or leave it here and then kind of go to a new share where I go to Laird and kind of show you them, because I think that's a little bit better for this. If it will let me, hopefully. Oh, I see why it's not letting me. Okay. Get out of here. I have to go to, escape out of this. Go here. All right, if I can't get it in a second, I'll have us go to break and I'll show you on the way back. It's being uncooperative for me. It shouldn't be, but it is. Okay. How about we take a quick break and then we look at Laird on the way back, and we'll see where we're at there. Okay, so take 10, 15 minutes and I'll see you on the other side. If you have any questions, I'll be around.
Okay. I have
Yes,
two.
I owe you an email. I apologize.
It's okay. I figured out some of it
Okay.
through Laird. I was like, some of the stuff I like read, but when I was going back, I like found some other things. But so when you're dividing for one-tailed, you only divide the p-value, right?
Yes, you do not divide everything else.
Okay.
Just the p-value. Just the p-value.
That's what I thought. And then when I was thinking about that, when you write up, what were we talking about this? When you write up a one-tailed test and it's just statistically significant, but it's in the wrong direction, would you say this is a statistically significant difference or whatever? It's statistically significantly lower, but you would fail to reject the null because it's the wrong direction? Like you would have to make that clear in your report?
That's how I would do it. That's how I
Okay.
would approach that. I would acknowledge that while the p-value is technically less than alpha, since the results are in the incorrect direction, we fail to reject the null hypothesis.
Okay. I think that's all I have for now.
Okay.
Sorry for all my questions.
No, it's good. They're good questions. I appreciate them. Yeah, I remembered right as we were about to get on today that somehow there was an email and I didn't get to it. So I'm glad you asked. Yeah,
Thank you.
absolutely. Okay. Hi, are we back? It's a little hard for me to tell. Hi. Okay, yeah, I guess we're back. Okay, wonderful. Okay, yep, thanks. Okay, so here is what I wanted to show you, and this is the other way of running the Wilcoxon, and what I think is slightly preferable. And of course, you see this in layered under the Wilcoxon signed rank test under procedures. If you go down, analyze to non-parametric tests, and then choose related samples. Okay, so we're not going to legacy, we're just choosing related samples. You will pretty much get what you get for the band Whitney U, and you can automatically compare observed data to hypothesize. Go to fields, bring over carb versus carb protein. So before, after, pre-test, post-test, bring over those two things. And then you could go to settings and make sure that it's set to run the Wilcoxon, but it should pretty much do that for you. And then you would click run to generate the output. If you were to do, that's the legacy. Want to see interpreting results. Okay. Hopefully this will. Here we go. This is what you will get out. And it very nicely tells you whether or not to reject the null. Of course, you have to be, I was just talking with someone before that you have to be, okay, puppy just joined me, 2 puppies just joined me. Okay, sorry about that. You have to be a little bit smarter than the machine in that if it's one-tailed, you have to make sure your direction's right? So remember to always check that. Even if it says to reject the null, you know, you might know better. And then if you double click on that table, all of this other stuff pops up for you. So this is the actual Wilcoxon test, your Z, and your p-value. So that can be kind of helpful. And then just to look at their write-up, I always switch over to APA because that's what we're, of course, interested in. And this is just a very nice, I won't read it out loud to you, but it's a very nice write-up of how to report a statistically significant result or non-statistically significant result. And it actually does a different example for a median difference between 2 conditions versus a difference over time. I know we've been primarily talking about over time, but like the people drinking the sports drink, the protein drink versus the non-protein drink would be a condition, one that's kind of more conditioned. They're still doing it at 2 different times, but we're not interested in pre-test, post-test in that case. It's that we have the same people doing different activities. And they were even counterbalanced the order. So some people did the non-protein and then the protein, and some people did the protein and not the reverse of that. Okay, so you can do it that way. So it can be a pre-post, or it can be 2 different conditions, but you got to have the same people doing both conditions. Okay, hopefully that, ask me questions if you have any about that. So I'll let you look through that piece. The only other thing I wanted to go through today, or to offer you, is that I did post a couple of data sets for you to play with. If you wanna, so you can, if you want, I'll give you a choice. If you want to play with those, I'm happy to like set up some breakout rooms for you, and you can play with them if you want to just, and we can talk about them. If you want to just take them to go, that's fine. If you want to use some additional time to ask me some questions today about some of the material, that's fine too. So why don't I just go ahead and create some breakout rooms? The data sets are under data sets in D2L for this course, and they're exercise 8.1 A and B. You should see that there. Let me just double check and make sure. And I apologize, someone pointed out that I had the wrong lecture posted. So I had actually posted an older version of the lecture. You could have found what I was talking about at the end, but I didn't realize that's what was going on. So I apologize for that. The correct one is now posted. Under data sets, it is chapter 8, exercise 1A and chapter 8, exercise 1B. So I'll set up some breakout rooms. If you want to play with that now, you can, doing the appropriate either t-test for dependent samples or Wilcoxon. If you want to hang back here and either answer or listen to questions, you're welcome to do that. If you are done for the day, I'm fine with that too. So let me set up the breakout rooms. And so for next time, before I completely open these, now I want 6 rooms. Make sure you have completed t-test for independent samples article, Man Whitney U article, and the homework that you'll be getting later today. Okay. And I was asking that you finish the t-test and Man Whitney homework by this Saturday evening, if you caught that. So hopefully you're on track for that. If you're having issues, just email me and let me know. We'll talk about it. Okay, so I'm going to open the rooms and I'm going to let you guys decide which thing you want to do. Okay. If you're taking off, have a great week. Okay, I don't see people moving to the breakout room. So do you have some questions you want to ask? Or do you just want to stay here and work on the data?
I have a question.
Sure.
When you are using one-tailed versus two-tailed, do you have to like do anything different in SPSS, or is it just the way you report it?
No, there's nothing different. It's a great question. There's nothing different at all in SPSS. It's just the way you report it. And remember, the main thing you do is divide that p-value by 2.
Okay.
Okay. Yeah, Jenna.
You mentioned an R value for the Wilcoxon test.
Skip that.
Okay.
Skip that. It's not that big a deal, and it's not easily observable in the output. So yeah, I showed you where the rest of it was. You can find the other pieces, I think, but the R, yeah, just skip it. Okay. It's hard to see everyone. Okay. I'm happy to hang back if you want to like look through and see if you have any other questions right now, or if you want to play with the data, that's fine too. And if, like I said, if you're done for the day, that's fine as well. And I'll wish you a great week. Okay.